don't think there was any administrative stuff today. Actually, I guess just one small note. I'm probably not going to be doing as many extensions for the homeworks from now on. We've kind of extended a lot of the other ones a lot. We're a little behind right now, and I am somewhat doing it for the sake of the TA and somewhat for the sake of just everybody in the class, because the more times I guess I extend assignments, the less time you're going to have to do the last few assignments. And so just in the interest of not making assignment 9 and 10 be something that everybody has to do in like 2 or 3 days, I'm going to try not to push back things as much. The extra credit assignment that I mentioned before should hopefully be up soon. I have an idea for that, so that will hopefully be up within about a week or two. And I think that's about it for administrative stuff. Last time we talked a bit about linked lists and doing them recursively, and then we finished up a little bit of the code that we had started last week. And what I want to do is finish the recursive code and then also work on a way to sort things using a linked list, but not with the sort that we did last time, rather just a sort where you just insert things, kind of, which is not the most practical with a linked list, but the idea at least holds for other things. So we started with insert, at least last time, and we had this recursive version of it. What I want to do is 2 more recursive versions, a lookup and a deletion. The lookup should be pretty much the same as what we did previously. It's really just going to look it up instead of check if it's null. I think we just really need one extra condition. It shouldn't be too bad. And then the deletion will have to actually do some work here. Right, so let's just say if we're doing the lookup, recursively at least, then we have some array like this, or not array, linked list again with all these nodes, and they point to the next one. And then we have the head to it. And if we're doing a lookup, what we want to do is try to figure out where a certain object is in our linked list. So let's just say this is 3, 4, and 7. So if I do a lookup for, let's just say 4, what I want to do is figure out where the node that contains 4 is, and then return, in this case, a reference to it. But again, we could return like a Boolean just saying that it is there, or keep track of an index or something like that. But I think this is fine for what we're doing. And so if we're going to do this recursively, we need to think of it in a way where we are kind of doing the same problem over and over again and reducing it. And so if we have a linked list here, we're going to basically use the same sort of reasoning that we did for the insert that we did last time, which was if we have a given node, for the insert we were saying, well, we can't insert it into a list that has 3 many things, because that's not something that's like a base case. It's not something that's trivial and easy to do and has defined behavior. So what we did was we instead tried to insert something into the list to the right of it. And so we're going to use the same sort of reasoning here. We're going to check the current element, see if that matches what we're looking for in our lookup. And if not, then what we're going to do is recursively check the list to the right of it. Again, we said that a linked list is just a list of all these nodes linked together by these pointers called next in our code. And it has a pointer to the head, which is just the start of the list. And so if I was to just cut off this 3 and ignore it completely, then the thing to the right of it is also a linked list, just a linked list that is smaller by 1. And so any operation that I can do to this linked list, I can also do it to the linked list that's to the right of the current node. And so what we'll do here in our code is we're just going to look and see if the current element matches, and if not, we're going to search the thing to the right of it. So we'll check that here. We'll say if the current node, so we have two parameters here. We have the object that we're looking for. In this case, we've limited our nodes to be integers because I was having trouble with generic types for some reason. And then we have a node pointer to whatever the current node is that we're checking for the value. So what we want to do is we want to check if the current value's data, the thing that's actually holding, is equal to the thing that we're looking for. We'll just say object. Then we found a match. In which case, we're just done. We can return that thing. So I'd say we'll return current. And then we would say else, and then we would need to go and check the list to the right of this, we said. So recursively, that would be lookup. We would just call the function itself, and we still want to look up the same object, and then we want to look it up in the list to the right of this, which begins in the next pointer with the pointer that's pointing to the list to the right of the current node. So that's what we would have to do recursively in order to find it. Now there is one thing that we should probably add here, which is just if we don't find it, we should probably add a case for that. And so if we didn't find it, then again, we have some sort of base case that stops us and finishes our execution. And in this case, something that is trivial to solve in terms of lookup is again, if we have a list that's just of size 0 that has nothing in it. And if that's the case, then we can never find anything. If you do a lookup on an empty list, you're never going to find what you're looking for because it's impossible to find something in something that has nothing. And so that would be our base case for this one. So if we say if the current, oh, whoops, and I typed that backwards. Else if the current data, I'm sorry, not current data, current next is equal to, I guess we'll just say current. If current is equal to null, which would tell us if the head pointer that we're currently using is null, then that refers to an empty list just by our definition that we gave before, and by the fact that we're at the end of the list, then that tells us that we have encountered something that we can't finish, in which case we should return some sort of error message, either throw an exception, or in this case I'm just going to return null because I think that's what we did with the lookup. Although I think I'd used null pointer, so maybe I should be consistent here and do that. Right, so we kind of have two base cases, I guess, is another thing to consider about this recursion. We have a base case where we have the trivial case of there's a list with nothing in it. You just can't solve that, no way to do it. And then we have the other case of we have a list that contains the object, which is this one here. And then our third thing, which is, again, the recursive case that we have in all versions of recursion, which just is saying, well, if we weren't able to solve the problem now, let's try to solve it with a smaller version of the problem, i.e. a list that's one smaller and to the right of our current list, or current head, at least. So that should solve our lookup recursively. And then the last part we have is deletion. Now, if you remember when we did the deletion, the explicit normal way with a loop in the last class and the class before that, we had to keep track of both a current node and a previous node, and we had to do that because of the way that deletion works. So remember, if we wanted to delete something like 4 here, then what we had to do is we had to, if we want to remove this, rather than just cut it off, we said that the pointers aren't going to go to the right place because 3 is still pointing to 4 even though it's removed, is we needed to keep track of whatever the thing before we're deleting is, redirect its pointer to point to the right of whatever we're deleting, and then delete it afterwards. And so as far as our actual code goes, it's going to be essentially the same as lookup because that's kind of our first step of our deletion is find the thing that we're deleting. So I'm just going to go ahead and copy and paste this code. It's going to be essentially exactly the same, except we're not going to return anything because it's void returning. And our recursive case will need to call the deletion function instead. I think I'm meaning to put list in front of these as well. I'm just now noticing. There we go. We'll call the deletion using the same object, and then we need to update our current and our next. So our current is going to equal this, and then I'm going to say that our previous equals the current. And I think that's fair. So this will do traversal in exactly the same way that we did via lookup, because lookup and deletion are really just the same. It's just different once you find the thing you're looking for, returning it versus removing it. And then we'll just replace the return code, which returned the correct answer, with the code that actually deletes it. So, oh, whoops, I'm meaning to put equal there. Let's make sure that's there for both of them. What we'll want to do then is, like we said, just make the previous next equal to the current next, and then delete the current to free the space. Which is really just the same thing that we did when we found our thing when we were doing the deletion the normal way. Now, there is one thing that we have to concern ourselves with here, which if you remember, there was a special case when we're deleting, which is if we delete the head, then that's not necessarily going to work correctly because of the fact that, like if you were to cut off this head, so let's go back a little bit. If you were to want to delete 3 and say it instead, let's say, then when you remove this, our condition kind of breaks here because we say the way our code works when we're deleting something is that we take the thing to the left of it and make its pointer point to the thing to the right of it, like redirect around it. But there is nothing to the left of a head, therefore our code doesn't work, and therefore we have an edge case that we need to address differently. And the way we said we did that is we just instead made the head point to the other direction, like the thing that's in front of it, because that's the new head once you delete the old head, and then just delete it like normal. And so we need to address that in our recursive code as well. I'm sure there's a bunch of different ways you could do that. You could do it before the function call, I suppose, and maybe make a wrapper like we did in that one class, but I'm just going to do a check here and see if it works. So we're saying if current data is equal to object. So let's just check if the current thing that we're actually deleting is the head, in which case we just delete it. So we'll say if the current is equal to the head. If they're the same pointer, then we need to instead make this so that the head is equal to the next one in the list, and then else we can do our normal code. And then the deletion is shared between both of them, right? We want to delete something regardless because that's just the nature of our deletion. And so these should work all fine. I'm going to rename these a little bit. I'm just going to put the word recursive in front of them, just so that it's clear for later. Even though it works without it because there's a overload. And let's just double check that this actually works. So here, let's just make a second example and make sure that our code works. So we'll say list, recursive list, and then we'll just throw some things into that. Oh, it seems to have an issue with what I'm doing. I wonder why. Too few argument. Oh, right. Because we need to specify the current. And we can't actually do that. So we'd either want to make a wrapper function like we did that one class, or I'm just going to make this have a, what's it called? I'm just going to make it have a public getter. I think that's probably just easier right now. So let's just make a public node pointer get head const that just returns the head. That way we can just grab the head and pass that as an argument. Okay, so we'll call dot get head. Throw that in here. And then let's just print it. I think that's fine. Did we make a recursive print? I suppose we didn't. And we totally could, but I guess it's alright. We'll just leave it. We'll hope everybody gets the idea of traversing recursively. Because really it would just be the same thing, except instead of deleting or instead of doing a lookup and returning like we did before, we would just print instead. It would just change really like one line of code, remove the if statement. Okay, so we see it run, and list.print. Oh, it would help if I actually did the recursive list we just made, not the one we had before. Let's actually do a deletion here too, just to test that. So we'll say recursive list dot recursive deletion, and then I guess we'll just delete 7. Wait, that's not even the number that's in there. 8. And the current node will need to be the head. And then I'm going to make the previous node null pointer, because when you start doing this recursively and you consider that there's a previous, then there is going to be no previous by default, because the well, there is no previous one to a head. So I think null pointer is just a good baseline for that, since we're going to overwrite it anyways in our recursive calls, if you remember. And then we'll just print it again. And it seems to error out, so I must have made some sort of mistake. Oh, it's the order I'm checking things in, I think. Current was null pointer. That's my bad. I think we should check this in the reverse order. And the reason I say we should do that is because it's going to need to check the contents of current, but if current is a null pointer, then that's going to be a null exception. So I think it's safer if we check that it's null first and then return. That's probably my issue. Although it shouldn't have errored out here. So I'm not entirely sure why that was the case. Let's try it again really quick. I wonder if it's because of our insert. Let me try double checking this. So if current equals null, I realize we never set the head, so that's probably the issue. So if current equals null, then put that in there. Yeah, I'm sorry. We need to add that. So this was the code from last time that we wrote, right at the end of class, which did insert. But remember, if we have an empty list, then we also need to set the head variable when we're actually inserting something into our list, because the head represents the top and it's like a separate variable, so we need to set it. Here we set the current equal to that. And I'm going to say if the head equals null, we'll make the head equal to this. So we'll create something new and then put it in at the head, and then else we'll just do the normal insertion. So I think that's actually our issue right now, is that I just wasn't setting the head correctly. And if we do it, yeah, that seems to fix it. So it says 5, 8, 10, and 12, which I think were the numbers that we had here. Right, 5, 8, 10, and 12, it prints them, and it does a deletion of 8, now it's gone, and then it prints the list a second time. Right, so we seem to have recursive ways to do these too, right? Whenever we are able to do something with loop, we can also do it recursively. In this case, I think it's maybe not the best idea to do it recursively, because it seems like overcomplicating the problem, but it definitely is an option that we have for things like this. Now, there's one last thing I wanted to do, and we can either do it recursively or just explicitly, and we'll probably do it explicitly. But I wanted to give an alternative to sorting with a caveat that it only works in certain cases, or it's only useful in certain cases, really. With the deletion that we had last time, or sorry, not deletion, with the search and sort that we had last time, it was a little complicated, the code was. And so what I want to do is give a way that is A, maybe a little bit easier to understand, and B, is potentially faster, given that you know in advance that you want the thing to be sorted always. So in the case of last time, we called the sort function partway through the life of the list, right? We created some list, and then we said list.add, whatever we want to add to it. Add 7. And we didn't really care about the fact that it was in order. We were just adding things to the list. So this would just create a list like this, and that's totally fine. We didn't really care about the order. And then we gave ourselves the option to go ahead and sort it later using some sort of sort function that just sorted the list. Now, if you know in advance that you're going to want the list sorted, you can actually do some sorting at the time of insertion, or I just called it add here, but you can do sorting at the time of insertion, and that will prevent you from having to do any sort of sorting later. Now, in terms of runtime, it is still going to be as bad as the sorting. It would take the same amount of time in terms of like complexity, if you're familiar with that, but it does at least allow you to do it in advance, I suppose. And so what I'm going to do here is, let's just say we wanted to insert 3 numbers. Insert 6, and then let's just say we call the same thing again here. So we'll say we insert 8, and then we insert 7. And then I guess 4. Let's do 4 numbers. Okay. So as far as our initial insertion, we're going to do this in exactly the same way. We're going to keep a head pointer, and by default that's going to point to nothing, aka null. And then whenever we do an insert, we just put whatever it is that we want right there, right? 6, and then have it go in. Now what I want to try and do here is, as we insert things, let's try to make it so that the things that we insert go to the correct place in order. And by that I mean least to greatest, or non-descending order. Non-descending. Which will work for the 8 here. So let's say we go and insert the 8. We would put that in, and then, assuming we understand how the insertion code works, it starts at the head and then traverses till it hits the end. It makes a new node with 8, makes a point to it, and then sets it equal to null. Right? But let's say we go and insert this 7. If we want this list to be in order, then during this insertion, the 7 is going to need to go right here, between the 6 and the 8, and not at the end where it would normally go if we did a normal insert. And so what I suggest we do here is we check what order the things are in terms of our traversal, and then try to insert based off of that. So what I propose here, if we want to insert the number 7, is just like we had before. Let's go ahead and make the node, make its tail pointer equal to null, and then what I propose we do is we start counting at the head, and we go until we hit something that would make it out of order if we put it afterwards. So if we start at the head here, we would want to insert the number 7, and we would say, well, is 7 less than 6? And if that's the case, then we're going to put it in. And if it's not the case, then we're going to keep trying until we can actually insert it somewhere. So if I want to put 7 into this array, then, or sorry, linked list, then I can't really do that if I'm encountering the number 6, because we don't know if the thing to the right of it is going to be still smaller than or equal to 7, and so we should probably keep checking. So we would check, is it equal to 6 or greater than, sorry, less than 6? No, so we would keep trying, go to the next part, and say, okay, well, is it less than 8? In which case, yes, it is. And once you hit that point, that's when you know that it's safe to insert it into the list. In the case that we encounter something that is greater than our number, we're going to need to put it before it in the list in order to have it in the sorted order. And then we're going to need to update some pointers. So consider, if I want this list to be in sorted order, what I need to happen here is I need the 6 to be pointing to 7 and the 7 to be pointing to 8. And then at that point, the linked list that I have is now sorted. So essentially what we need to do is, again, we need to keep track of some sort of previous information, because we are keeping track of both what the last node was and what the current node is. So we'll keep track of some previous pointer that points to whatever the last node is that we checked, and then we'll keep another pointer as we traverse the array, or sorry, linked list, that points to whatever the current thing is. And so what we need to do here is, remember we had this before where 6 was pointing to that 8. What we want to happen instead is we want the 6 to be pointing to the new thing that we're inserting in the correct order, and then have that 7 point, instead of to null, to whatever came to the right of it now. And so that code is very similar to our deletion code. We're going to set the previous next pointer equal to the current thing. And then we're going to need to set the pointer field for the thing we're actually inserting to point to the thing to the right of it. So this would be, I should probably write this all in black, but I'm writing it in green. We would need to set the thing that we're inserting. So let's just say we call that the new node. We'll give it a name when we actually write the code. And we'll set it equal to, we'll set its next, the pointer field it has, equal to the current thing, which is the thing to the right of it. And in that case, we should now have both these arrows pointing in the correct direction. One pointing to the start of this, and then one pointing out of the end to whatever the next thing is. We'll again have some sort of special case here if we're trying to insert at the head. So we have kind of a mess here, but let's say we had all this stuff. I'm going to go to a new page, and we've inserted it correctly. And we have 6 and then 7 now that we correctly inserted by the code we just did. And then 8, and then that's the end of the list with the null at the end here. And we wanted to do the rest of that code we wrote, which was to insert the number 4 next. Now 4 is an example of a special case because it is not going to go to the end like the last one, so we're going to need to do something a little early, a little premature, and just kind of insert it before we get to the end of the linked list. And it's also special because 4 is less than all of the numbers we currently have. So if we want to keep this in sorted order again, we're going to need it to go at the very beginning, which means we're going to need to replace the head. If this is the case, we need to check if the previous thing that we were trying to insert it to just doesn't exist, because again, there's like nothing to the left of a head, just nothing exists there. So we can check either if the current node, which is the one, if you remember, that we're checking, is it less than, if that one is the head, or we want to check if the previous, which just doesn't exist because there is no previous here, is null because there's no left, there's nothing to the left of the head. That's our condition. If we check that, it ends up being true. We know we're inserting into the head, and in which case we should make the node like we normally do. So make a 4, have the head point to that instead, since it is going to be the head of the list now, and then have this point to over here. So we kind of have one special case, as we do with a lot of these, when we encounter something that needs to update the head, and so we'll need to adjust that too. But you'll notice as we do this, it becomes a little bit nicer because you'll notice with both the 7 and the 4, I read that a little too fast. Both the 7 and the 4, they got to their location that they actually need to go into the linked list faster than if we were to insert them normally. So let's just go back to what we had with the 6 and the 8. We had this scenario, and we wanted to insert the 7 into the linked list. And what we ended up doing is 7 needed to go between 6 and 8, which meant in the long run we ended up traversing exactly one node. We passed the 6 and got to the 8, and then we were done. But normally, when we do an insert where we're not trying to sort things while we're doing it, we would actually have to go always to the end of the list, which in that case would go past both the 6 and the 8, which would be 2, right? And in the case of our 4 here, we only did really like 0. We started at the first thing and just put it straight in. Versus if I was to insert this 4 to the very end, it would go 1, 2, 3. Okay. If you do this insert where you want to sort things, it ends up being a little bit faster potentially. Again, it still has the same time complexity in terms of like the insert, and the sort is the same time complexity as if we did bubble sort, but you actually save a few steps in doing it potentially. And it might not matter here in this example, but if you have a list of 100 things, then that can help a little bit. And this is kind of important because that's the weakness of our linked list in general is the fact that we have to traverse the whole thing every single time if we want to insert something, or if we want to do a lookup. It's not like an array where you can just jump straight to where you need to go whenever you are looking something up, potentially, just depending on the scenario. We always have to start at the head and like follow these pointers along till we reach the end. So that addresses the issue a little bit by making us not always go to the end, and so it's a little bit faster potentially. And it also gives us the advantage of putting things in a sorted order, which is nice, potentially. So if you have a scenario where you want things sorted, or it's okay for things to be sorted, I think this is a better kind of insert to do. Let's just go ahead and write the code for that really quick. And then I think we'll be done with these singly linked lists. Again, I'll put this on Canvas at some point. I'm just going to add some comments so that it's a little bit easier to read. Let's go ahead and write another function called void insert. Let's say insert in order. It takes an int object and then inserts it. And then go ahead and write the code here. Okay, so in much the same way as our other code, we're just going to want to traverse it exactly the same way. We're going to keep some sort of pointer that represents the current and then just have it update. I'm just going to copy and paste some of this code. In fact, let's just grab this whole thing. You'll notice that I've pretty much used this exact same code with just like tiny variations for every single function we've written. And so it's really good to remember this for the future assignments, I would say, even if you don't use linked list all that much in actual programming. And then I want to keep track of the previous pointer as well, which we'll call null pointer, and I actually need to make it a pointer. Okay. So we have those. And I'm going to make another node really quick, just called new node that represents the node that we want to insert. Since we're always going to insert something, then it's okay to just create it beforehand. That's totally fine. And we'll create it with the object. And then we have this traversal here. So while current is not equal to null pointer, i.e. we're not at the end, then we can keep updating. Okay. So we should probably keep this at least. I'm going to update both the current and the previous. Remember, the order does matter on these. I'm going to set the previous equal to whatever the current is and then make the current equal to the next thing. And then we need to do our actual checks that we were saying here. So what we were saying is we should check if our insert would make this out of order, i.e. if we like made a number that's smaller go to the right of something that it shouldn't, then we have an issue. So the way we were doing that is we were checking if the current data is greater than the thing we're trying to insert, which we'll just say is the object. Then we can do our insert. Right, so we said the way we're going to do that is we're going to make the previous point to the new one that we're creating, which are called previous, not prev. And then we said we want our new node that we're inserting to point to the object that's going to go to the right of it, which is going to be the current. It's going to be some sort of exception, dereferencing null pointer previous. Fair point. So it's giving us that warning because I'm not checking for that case where if we were to try and insert into the head, we would have an issue. Let's go ahead and address that really quick. So we will say, I guess we'll just do that up here. Let's check before we even do the while loop. That way we kind of push our ifs outside of a loop, make our code a little better. We will say if the head data is greater than what we're trying to insert. So similar to the for that we had, if the data we are trying to insert is smaller than the head, i.e. it's going to be the new smallest, the new head, then we need to do something special, which is we will set the current heads, no, I'm sorry. All we have to do is set the new node's next pointer to point to the head, and then update the head to be the node that we just inserted. And then we can return. Now I guess if I do this outside the loop, then I probably want to update this a little bit. So let me move this down just a little bit. This implies we've already checked the head, I guess, so we can start the list at the thing to the right of the head. So I'm just going to make this next here and then make this a head, and that should make our compiler error go away. Okay, so that should be all right. And then now I think we have one extra special case we need to worry about, which is the tail. So let's just double check if that works. So if the current does not equal null pointer, so we have the biggest thing. Let me add a return in here really quick. I think just to be safe, let's just check this. If we break out of this condition, that's if the current is equal to null pointer, i.e. we got to the tail, which would mean that the previous is pointing to the tail and the current is pointing to null, because that's the condition that breaks this. I think let's just add an extra case in here to add things to the end of the list, just in case that's where it belongs. And we would then say that the previous next is equal to the new node that we created. And if you kind of consider it, this is really just the same as the default insert behavior. We got all the way to the end, and if you get all the way to the end, all you need to do is make the previous end point to the new end of the list. And that's really the only single operation we have to do. So this should work, I believe. Let's go ahead and test it out really quick. Let's do one last thing. Just write some code here for sorting at insert time. Let's create one last list and just call it sorted. And then we'll add things here. So we'll say sorted dot insert order. And then let's just try some things out here. See if I'm going to put 5 things in. We'll put 5, 7, 6, so we have something that goes in between them just to make sure that that works. We'll put in an 8, and we'll put in a 4 so that we can test that the head works. And then let's just print it. And hopefully what we should see here is that it should get all of these numbers in order and print them and not crash, hopefully. Well, I think we got everything but the crash. Head was null pointer. Ah, I keep forgetting to do this. Right, we said if the head is null pointer, then the list is empty, which is a special case. So let's check that really quick. Let's just say if the head is null. I don't know if I can spell. Then I guess that's kind of trivial. We just put the new node where it belongs and then return. So it seems to be mostly correct, but the 7 is getting lost. So the 7's not appearing. Let's try to figure out why that is. So let's say we get in here and the 7 is what we're inserting. And we need it to go between the 5 and the 8. should ideally be this case, right? Oh no, it should just go after the 5. It's disappearing somewhere. Let's just check. Let's check this really quick. I think I may have made a mistake. Where'd my window go? Oh, there it is. 5, 6. So the 7's disappearing once we add that in. Oops, didn't mean to hit that. Okay. So we get 5, 7. So the 7's getting inserted correctly. I think I just have a mistake with one of our cases here. So let's check it. So saying if current data is greater than object, then the previous next equals the new node. Oh, whoops. I'm sorry, that was a typo. That should hopefully fix it, right? 5, 6, yeah, okay, we see everything. Okay, my bad, just forgot to finish typing that. But you can see here from our print that when we do it, even though we inserted these things in an order that was not sorted, inserted 5, then 7, then 8, and 6, and 4, we end up getting a case where they are in the greatest, or least the greatest order. So you can kind of save a little bit of time doing insertion as well as sorting this way. And this philosophy carries over to things like heaps. If you're curious, I would encourage you to Google something like heap sort, although you should probably know what a heap is first. And we can sort things as we do insertions, which is kind of interesting that you can use these data structures as a different way to sort. So you have an alternative to something like bubble sort or selection sort, where you have to have a list that already exists and then run through that whole thing and then sort it. You can kind of go as you're creating it and go with like this online kind of strategy. By online, I just mean like you can update it as your program is running and sort it as it goes. So, you know, if I had a program where I read 3 numbers and then the program runs for a while and does some stuff and then the user comes back and types some more numbers later, if we were to do something like bubble sort or selection sort, you have to sort every single time a user enters new data, right? Which becomes very expensive computationally because you're going to have to keep calling that sort over and over again and make it do bubble sort every single time. But if you have a data structure like this, where it sorts it at the time of insertion, then you can save yourself a little bit of time because it's already A, mostly sorted when you do the insert, and B, you can kind of save yourself some time on the insert itself. In practice, just if you're wondering, you would almost never actually do this with a linked list. It's almost entirely impractical. Linked lists are generally not something you use a lot, but there are other data structures where you can use this philosophy, like the heap I mentioned, where it actually is useful. So just be aware. Linked lists aren't super common in practice, but this is at least like an introduction to something that would actually be useful. Does anybody have any last questions on these singly linked lists? I know we've covered a lot. It took us a few classes. So if you have any questions or you want me to review on insert or deletion or anything, please let me know. Okay, fair enough. I don't see anything in the chat, so I'll assume there's no questions. I'll post this code a little later. I think we want to do one more thing with the linked list, although it's just kind of a variation on this. I'll just close this. We'll maybe program it a little bit, depending on if we have time. It shouldn't take all that long. and it's not really that different, so I don't know if we'll actually write a program for it. But we've noticed that there's one issue, or actually a couple issues with the linked list. One was that we have to go all the way from the beginning to the end every time we want to do an insertion, at least if we're not doing that sorted version that we just did. So let's just address some pros and cons here. The pros are that it's not contiguous. I guess that's both a pro and a con, so I should be more specific. It's not contiguous, which means that we can store these separate, so it doesn't require a reallocation and a copy like we would have if we did a dynamically allocated array. Because if we run out of space in a dynamically allocated array, we have to make a bigger one and then copy everything over. So it kind of solves that issue because we just allocate very small amounts of memory and then chain those together. We don't have to reallocate every time we insert something new. We just do one allocation and then we're done. We only ever run out of memory if the entire computer runs out of memory, which is pretty rare. That's pretty good. And that's about it. I guess it's a little malleable. You could do some things like our insertion. I'm just going to use the word malleable. That's not a technical term. But with our sorting, we were able to insert things where they need to go. So again, if this was like 6 and 8, I can just insert the 7 straight here, and it's able to go there. We're also able to use it to replicate other data structures that you'll see in some of the coming classes. So it has some flexibility. We're able to make it work in ways that an array couldn't. Because if I wanted to do that same strategy with an array, let's just say we had this 6 and this 8 here, and I want to insert an array. Let's actually say there's 6, 8, 9, and 10, and I go to insert the number 7 in between these two things. Then in order to do this in an array, I need to make sure that there's enough blank space and then move the 10 over, move the 9 over, move the 8 over, and then put it in, which is really time consuming because we have to copy, how many ever things are to the right of what we're inserting into our list. So that's kind of bad. This requires like shifting 3 things. Whereas if we do it here, then if I just want to put the 7 in, I just put it straight in and just update the pointers, and I don't need to rearrange everything. So there's some advantage there to that. So that's what I mean, I guess, by malleable. I'm just throwing out that term. So it has some advantages over arrays, although some of the cons were that the traversal is slow. Every single time we want to look through this, we need to start at the head and then work our way through. So that's kind of an issue. And I'll just specify that that means the lookup is bad compared to an array, at least relative to an array. When you have an array, if you say, I want to go grab the thing at index 2, you just go to index 2 and grab that number 9. But if I want to go to the index 2 here, then I have to start at the head and then go through this one and then go through that one and then go through that one. And so it's a lot slower than just doing an array. So lookup is pretty bad, and it also only goes one way. So even if I came up with a solution to this, which I will propose one in a second, then we still have the issue of only going one way, which might matter in certain cases where we need to do some sort of complex operation on the linked list, where once we follow this thing, we're not sure. Oh, so I see a student saying they can't hear anything. Is everybody able to hear me so far? Or is it just right now that it broke out? Okay, you can hear me. Okay, so it might just be an issue for one student. Okay, fair enough. Okay, cool. Thank you guys for letting me know. Where were we? I should probably wait for the student to rejoin. So. And if it doesn't end up working, sometimes you have to readjust the audio settings in WebEx. It's a little weird sometimes. I guess in the meantime, at least this will be on recording. Right, we were talking about the one-way aspects. And so a disadvantage of a linked list is the fact that you can only go one direction. So even if I solve the first problem, which I will, then if I was to follow this pointer and end up at the 8 from the 6, then I can't go back to the 6 anymore because this arrow only goes one direction. And if I ever want to go back to that, I need to restart at the head and count my way back over, which was kind of why our sort in the last class ended up being so complicated, was because we couldn't just do that, at least not easily, because it would be very, very slow and require us to do the whole traversal every single time, which is what I was trying to avoid. And that's just not good. So it's only one way, which is a bit of an issue. Oh, for sure, no worries. So that's our issue. Is it's one way. We can only follow these pointers one way, and the traversal is super slow. So what I want to do is at least come up with some issues for this. Oh, sorry. One last thing. The one way also played into the way we had to do deletion. If you remember, when we were doing deletion, if I was to delete this thing, then we had to always keep track of some pointer to the previous node before the thing we're deleting so that we didn't accidentally make some sort of mistake with it. And we wouldn't have to keep that extra variable if we were able to go backwards, because we would just know what came before this, right? So what I want to do is solve both of these problems. The traversal being slow, we can somewhat fix. So this is just unavoidable, really. You're kind of stuck with this no matter what. When you're doing a linked list, there are better data structures that avoid this. But if I just, was having an issue with my insertion, let's just say specifically, then when you do insertion, that always goes to the tail, assuming we're not doing the sorted version I just did, which means that you could just keep a pointer to the tail and update that every single time you do an insertion, and that would be fine. So this kind of solves that problem, at least in the case of insertion, which is fine. And what I want to do now is try to solve the other problem, which is the fact that these pointers only go one way. What they'll do is we will create a second kind of data structure, which is just a linked list, but with an extra thing. Sorry, that's a typo. A doubly linked list. And the only difference in this thing is that it's going to keep track of not only the data and a pointer to the next thing, but we're also going to keep track of a pointer that goes backwards too. We'll keep track of that. So now it's going to have 3 fields per node. So the node will have some sort of data. We'll just say it's some abstract data type we'll call T, and then it's going to have 2 pointers now in order to do a doubly linked list, which is going to be one that points to whatever the next thing is, and one that points to whatever the previous thing is. And then as far as our list goes, we're going to keep track of a head again. We can keep track of a tail if we want, and that's probably fine. I'm just going to keep it a head for now, and we'll go ahead and do this. So now we're going to have whatever data is stored in here, let's just say integers in this case, and then this will go in both directions. So this ends up making deletion a little bit easier, as well as some of the other operations that we might end up doing. It probably makes the sorting a lot easier, honestly. And yeah, it's a little nice. Now, one thing, because we've been marking the end of these lists by having a null pointer point to the right, we're going to do the same thing with the head. So in order to check for the head, we're going to have its left pointer, the previous pointer I'm going to call it here, be set equal to null if it's the head. And so that's just something we have to keep in mind as we do these things here. So let's just go over the operations again. and what's different when we do them in this case. So we'll again have an insertion, a deletion, and then a lookup. Now insertion, as far as initializing the list, is going to be exactly the same way. Remember again, if we have an empty linked list, the way we designate that is we just say it's pointing to null. So in order to insert something into an empty linked list, we create it and then overwrite the null with whatever we created. And in this case, whenever we do an insertion on any kind of node, we're going to keep both the previous pointer and the next pointer equal to null. So this is both the beginning and the end of the list when I do one single insert. Let's call this 0, I guess. And so the creation of a new object is exactly the same. We just create it and make the head point to it when the list is empty. When we do a normal insertion after that, it's really just going to be exactly the same as the linked list that we just did. We just have maybe one extra thing we need to set. In order to do this, we will start at the head, we will point to it, and then we will check if we're at the end of the list. Once we hit the end of the list, we will go ahead and just update its tail pointer to point to whatever the new thing is we created. So that's how our previous insert worked. We just move to the end of the list, starting at the head, traverse our way to the right, and then eventually when we get there, we just put the thing at the end. And so if we were to kind of consider this as just a singly linked list that we've done so far, then this looks exactly like the singly linked list. Now the only exception we have to do is that we need to make this point backwards here. We're just going to have that point backwards. Okay. So that's our only exception. The only thing that we have to do on top of our normal insertion is just make the pointer point back. Insertion is pretty easy, basically just the same thing with one extra line of code. The lookup, I'm not even going to write out, it's just exactly the same. Let me draw a little picture, but it's no difference in the code. If we consider what a lookup does, it just goes and finds the thing and then returns it. Say I have this linked list like this, doubly linked list, and then I have this pointing here and that pointing there, and then I have the number 4 and 7, and I do a lookup on 7. Then the fact that we have pointers going both directions doesn't matter here. It doesn't change the way that we do this. We just start at the head and follow it right until we find what we need to find. We never need to go left or set anything extra when doing a lookup because we don't set anything in general. It's just, a lookup, we go to the thing and grab it. So a doubly linked list versus a singly linked list, the code is exactly the same for the lookup. There's no real difference there. But the deletion, we will have to update pointers. So we'll actually need to keep track of that. So let's say we go ahead and do the deletion. We're again going to have two cases like the normal deletion that we had, where we need to address if we're deleting the head. And if you were keeping track of a tail, you would need to have a special case where you address if you're deleting the tail, but we're just going to say we have this. I'm going to do 3 nodes this time. It'll be pretty much exactly the same code, except this time it's actually, I think, a little bit easier than when we did it with a singly linked list. And that's because we have these arrows going both directions now. So let's say I want to delete whatever's here. Let's say this is 4, 1, and 7. If I was to call delete, and I wanted to delete the number 4, then what we're going to need to do is we're going to need to make these point around it, like we said. So originally with our deletion, we wanted to make the single arrow that we had just point around where the thing we deleted was to whatever it should be pointing to now, like the right side of it. Now we're just going to have to do the same thing, but with this extra part. So like the insertion, it's just one extra pointer that we have to set every time we do this operation, which is really not that big of a deal. But The nice thing about doing it this way is that we don't actually have to keep track of a previous pointer and update that as we go along in our loop, because of the fact that we have something that points backwards. If this is the head here, and then we kept track of some pointer, again, we'll just call it current, like the other ones we had, then if we go along and are looking for the thing that we're trying to find, so check this, see, oh, well, that's not 4, and then go and check the next one, see, is that 4, and then find it, we don't need to keep track of a previous, because now we know that the thing to the left of us, we can just follow this one pointer and get to where we need to go, which is nice. We don't have to worry about making things way more complicated. I mean, the previous wasn't like super complicated, but some of these operations end up being easier now. So all we need to do for that is, before we delete the thing, we're just going to set, we'll call it curs, we'll say curs previous is going to equal, actually, so as far as the diagram goes, it's way easier. The code here might look a little intimidating, I will say. What we want is, we want this to point to that, right? So first things first, let's address how we get to this thing. If we have the current pointer, then we know the previous is going to be referring to this node. So this part here, I'm just going to color it. This part here represents this guy, this one node. And if I had that orange node, what I want to do is I want to set its right pointer, the next pointer, equal to this thing over here. I'm going to take that orange expression, which will evaluate to this one node, add the word next to the end of it. And then what we want to do is we want to set it equal to this guy over here, which is going to be the next of our current thing. I have to apologize, it's going to go across 2 lines here. So this might look a little intimidating without the diagram, but this will set this pointer equal to that thing there. And then we need to do our other one. So I'll ask you guys if you can figure this one out. What do you think the first part is if we want to set this one? So if I want to make this point to the previous one, how am I going to get that? So first things first, how do I, if I know what the current is, which is this guy, how do I get the 7 node here? Give you a hint, we want to use the current pointer, and if we want the thing to the right of it, what is that called in the context of our code? Right, and so that was a private response, but you're right, we want that to be next. So in the context of our code, this purple thing that I have here, the 7 node, is going to be the next of the current node, because the next is always the thing to the right of it. So that will refer to the 7. And then what we want to do is we want to set this part equal to that part over there. So assuming that I have this expression which represents the 7, how do I get the left pointer of that 7 node? Right. So I see a response of current next previous, which would be exactly right. So if this purple part represents the 7 node because it's the next of 4, then the previous of this purple part, whatever it evaluates to, is going to be the left pointer of that purple node. And so this will get the thing to the right of it and set its left pointer. And what we want to do is we want to set it equal to this guy over here, which, if you remember, is that part, the cur sub previous. So I should probably add a little more color here. What we've done is we've taken the orange guy's next, so the orange part's next, and set it equal to the purple node. and then we went ahead with the purple node and set it equal to this orange node, or to have its previous point to that orange node. So, without the colors, it looks a little complicated, right? It's like 3 pointers. But if you kind of think about what this specific block evaluates to, being the previous node, this orange one, and the same thing with the purple one, the next being the thing to the right of it, then we can kind of reason out the rest of it. This is just a programming strategy I recommend in general for when you're doing object-oriented programming. If you have some sort of long expression, try evaluating and thinking of what just this part is here, and then like block out the fact that it's something that looks complicated in your mind and just say, well, this is that orange part. And it's totally fine to like go out on a piece of paper and write it down exactly like this. I know I do that when I'm programming something new for the first time. So this ends up setting our things correctly. So all we need to do was 2 sets. And conceptually, I think they're pretty easy, right? We just make these point to where they need to go. I just think these expressions are maybe a little hard to figure out if you're trying to do it the first time. And I'll try to post this image, hopefully. I think this program has an exporting feature, so I'll try to get it like a JPEG or something. Cool, so that seems to take care of our deletion. I might just write a quick program for this in between classes. It's really, I don't know, I don't think it's worth spending a whole class on. But that's our doubly linked list. It's basically just the same as a singly linked list, except it has a thing going the opposite direction, which fixes one of those cons. So I think that's about it for linked lists. I don't recommend them for almost anything ever, but here is just like a learning exercise. You'll use something that's better, or some other data structures that are better if you take the data structures course 302 that don't have all of these issues and are also just way faster. But they're also more complicated, so that's why we teach that one here. So we got about 5 minutes left. I don't think I want to start anything new. So I guess next time we'll talk about stacks and queues, I think, are the last 2 things we need to talk about. And then, yeah, I guess after that point, we'll start talking about whatever we have time to talk about, because that's really the only last 2 things on the rubric, I think. So I'll put up an announcement. If you have any ideas for things you want to talk about that you've heard about before, just let me know. We can definitely have a discussion, or we can talk about development, or if you wanted to learn a new language or something, we can totally do that. But I guess on that note, I'll stick around if you have any questions, and if not, I will see you all next week.